I think it's time to start. So thank you everyone for joining in. And especially thank you to Igor and Everest for joining in. Let me just introduce our presenters today. So this is today's prediction modeling presentation, and it's going to be Igor Shuryak and Everest Yang. And the title is Estimating Temporal Treatment Effect Trajectories with CAST, which is Causal Analysis of Survival Trajectories. So Igor is an associate professor at the Center for Radiological Research at Columbia University Medical Center. And Everest Yang is a computer science student at Brown University and the lead developer of the CAST framework. So now I think it's to you.
Yes, thank you very much for the kind introduction, and good afternoon to everyone. We are very grateful for being invited to give this talk. We're honored. So since you already went over the title and a little bit about us, I will just go to the outline. So we will start with motivation for this project, like essentially why we wanted to do causal machine learning type approach for cancer and potentially other diseases. And then Everest will go into the CAST framework itself and its first application, which was in head and neck cancer. And then I will talk about extensions to gliomas or another type of cancer and some broader context. So we already went over this. I think Diana kindly introduced both of us, so I will skip it. So for the motivation is why causal machine learning? So one of the most well-known theorists in causal inference is Dr. Judea Pearl from UCLA in California, and he wrote this book of why, among many other articles and books. And there is a three-level or three steps on a ladder type of classification that he established, and it's very useful. So level one is associational, and this answers questions like what is or what will happen. For example, patients who received a higher dose, say of radiation in this case, survived longer on average. And another question would be to predict the outcomes for a patient given features. So this is where a lot of modeling is used, including machine learning. And then the other layers are interventional. What if we act to change the treatment? For example, give a different treatment option, different treatment dose to this patient or this group. How would the outcomes change then? And then the most complex layer is counterfactual, is that we already know what the patient was treated with and what the outcome was, but we're imagining what would have happened differently if we go back in time and gave a different treatment to this patient. So the difference between these interventional and associational approaches is the target distribution. So for a prediction task, the distribution can be probability of outcome Y given the treatment T and the features X. Or it could be expectation of Y, but in general, that's the approach. So among patients with features X who received treatment T, what were their outcomes? And usually T and X are not specifically distinguished. They just go into the model as features, as predictors. And the model learns associations, but it doesn't structurally try to take confounding into account. And the causal approach involves this do operator, which also comes from Pearl. And what that means is you are trying to set the treatment to a specific value, which is called T star here. So instead of observing the treatment distribution, you are setting it to this dosage, this treatment option. And this, for example, could be not a very typical treatment option or dosage that this type of covariate profile sees. It should be within the support, but maybe not necessarily the most common one. And the reason where this makes a difference, for example, in oncology, it's relatively common that sicker patients with more advanced disease can receive more intense treatment, like more drugs, higher dosages, and so on. So naively, their outcomes can look worse than patients who received less intense treatment. But of course, usually it doesn't mean that the more intense treatment is worse, it's harmful. It's probably mostly due to confounding. So the idea is the causal ML attempts to estimate this interventional distribution from observational data. So it attempts to recover the treatment effects under causal identification assumptions that we will mention. But also usefully not only for the average effect, but also for some groups and potentially individuals. So you can investigate heterogeneity in the treatment effect. Is it actually the same for all patients or it varies by some features? So definitely this type of approach requires domain knowledge, usually a team effort of experts from the clinic, from statistics, from other areas that should work together and create a structure like usually this directed acyclic graph DAG type of structure where you write down and show what is affecting what variables are causing what. And general categories that should be in the model is confounders, which can affect both treatment and outcome. And we're interested, of course, mostly in this red arrow and the effect of treatment on outcome, but we need to model the blue arrows as well. But these other examples show that it's usually not a good idea to include all available features in the causal model because some of them can actually disrupt the estimate that you're looking for. For example, these colliders, mediators, and so on. So then also, what is actually causal in this causal machine learning type approach? Of course, it's still machine learning. It's not an experiment. But there are two layers. So layer one is the assumptions, the identification assumptions. And actually, this is not something specific to a given method. It would apply to all the methods if you want to interpret the effects causally. Like if it's a linear regression, it still would need these ignorability, positivity, Sutwa assumptions to interpret the result causally. And they're defined here. Of course, in reality, the toughest one is the first one, the no unmeasured confounding. Usually, this is not the case. Like you can try to measure as much as possible based on domain knowledge, but often there's something that's not realistically measured. But then, as we'll say later, there are many ways to do sensitivity analysis to try to address this. What are actually the effects of this violation? And the layer two is where the causal ML actually specializes. What it tries to do is to flexibly estimate heterogeneous treatment effects and average treatment effects. But it focuses on treatment effects specifically. So by comparison, some traditional methods like logistic or linear regression, in addition to these assumptions in layer one, they also, of course, have their own assumptions and their own functional forms. So all that needs to be satisfied. And especially modern type of medical data, like I wrote on the top there, is complex. There can be nonlinear relationships and a priori not usually known what they are, interactions. And also the data that hospitals generate is usually multimodal. There is not just tabular, but also imaging. On cancer patients, for example, a lot of imaging, a lot of text like doctor's notes and so on. So a model that can handle these complex inputs would be much more informative. And also methods with regularization, like for example, lasso-rich type of regressions are also common predictive ML, like random forest boosting and so on. They optimize for prediction, but the trade-off for that, they can actually distort or even drop in some cases the treatment effect if it's not the strongest predictor. So they focus on other variables which predict the outcome most. But in this model, you want the treatment effect to be the target. So these are the reasons for this kind of specialization. And of course, RCTs are still the gold standard, definitely, but realistically, they can't cover everything that doctors or scientists want to explore. So this is also a very useful field for this type of approach. So the original project that led to this CAST development was actually modeling tumor repopulation and head and neck cancer that we were working on for a while. So head and neck cancer is relatively common. It's a fast-growing cancer. So repopulation of the tumor during treatment has a big effect. It can definitely reduce tumor control. And this was known for a long time. So the classic mathematical model for this was actually developed in the UK by Dr. Withers, and this graph is from their publication in the 1980s. And they modeled repopulation using a fixed onset time, like about a month after start of radiation treatment, and a fixed rate. And at Columbia, our group was tweaking this model, trying to improve it. And what we introduced is we made the onset rate and the timing dose dependent. So try to make it more biologically plausible that it compensates for the intensity of cell killing. So we developed this model, applied it to various data sets. In general, as we'll show soon, is that higher BED, and that's a biologically effective dose. So that's what's used in radiation oncology as a function that maps those raw treatment numbers, like doses per fraction, number of fractions, to one continuous value. Is associated with improved survival, probably causally. But then we were wondering, how does this benefit change over time after treatment? So that's where the CAST came in, the motivation for it. So here are screenshots of our papers that we published on this example over a few years. And in general, what we found that increasing this biologically effective dosage under both models actually increased the restricted mean survival time, increased survival probability appreciably. And this is clinically significant life extension. If somebody is interested, we also made this website that calculates those BEDs, but that is oncology specific. And then that was the motivation background for CAST, and Everest will take over.
Hey everyone, thank you for having me. Now I'll be talking about the CAST framework. Next slide. So first, I'm going to talk about the gap as to why treatment effects are not constant over time. So most standard approaches, such as the Cox regression model, focus more on prediction and often assume treatment effects are constant over time. And causal machine learning methods improve this by estimating treatment effects. They do, but they still do it at fixed time horizons. For example, at 1 year or 5 years, etc. However, in oncology, treatment effects are dynamic, right? They can rise, peak, and decline. So the key question we asked in our study is, can we model the entire trajectory of treatment effect over time? Next slide, please. So yeah, as Igor mentioned, this was our CAST project. It was published at a few places, including 3 NeurIPS workshops. And I helped develop a good majority of CAST. So I'm really excited to share it with you guys. Next slide, please. Yeah, so before I talk more about the CAST framework, I want to provide some context on CSFs, or causal survival forest. So CSFs extend causal forests to handle censored survival data. And conceptually, they share ideas with causal forests and double machine learning. So there are a few steps. The first is to build the nuisance function, which includes propensity scores, censoring model, and then the survival model. These are all forest-based. And after that, you want to build the causal forest on pseudo-outcome residuals. And this includes using name and orthogonality concept, like in double machine learning. And some of the key properties here is that CSF was developed originally for binary treatment, and it now supports continuous treatment. However, like I guess the one small flaw is that it assumes a linear treatment effect per patient, while also allowing nonlinear confounder effects and interactions. And the reason why we need CAST on top of CSFs is because CSFs gives separate but not independent average treatment effects and conditional average treatment effect point estimates at each horizon. And these average treatment effect estimates at neighboring horizons are highly correlated. So what CAST does is it fits a flexible trajectory of both over the horizon time. And I'll talk more in detail about like the technical aspects of how CAST works. Next slide, please. So here is figure 1 from our paper. It's, I guess, a figure demonstrating the workflow of the CAST framework. So I'll walk through the figure step by step. On the left here on the right, this represents the clinical data. So this is all the raw clinical input and can include the demographics, tumor characteristics, and treatment variables from the RadCure data set, which is the head and neck cancer data set we use in this experiment. In this data set, there are real messy hospital records such as missing values and heterogeneous scales. And this section represents everything that has to be cleaned and standardized and also harmonized before any modeling is possible. Next, in the middle here, we have the causal survival forest, which is essentially like the causal engine of the entire project. Here, the data is split, it's propensity adjusted, and it's also passed into causal survival forests. And for each horizon between 12 months all the way through 120 months, we train a separate forest. And each model estimates counterfactual outcomes under treatment and control, and also produces a horizon-specific treatment effect with uncertainty. On the right here, we have the interpretable outputs. And what this section shows is that these horizon level estimates are still just snapshots, right? And what CAST does is it treats them as noisy samples from an underlying function of time. And the parametric and non-parametric modulus fit continuous trajectories over these points. So from these curves, we can recover interpretable quantities such as peak time, maximum effect, and decay behavior. And this is where the snapshots become a story. And in a few slides, I'll talk a lot more in detail about a lot of the, I guess, modeling techniques we used to get these interpretable quantities. And lastly, on the bottom here, we have our validation framework. And here we just want to make sure all of our results are legitimate and they're supported by these dummy tests. So here we inject synthetic confounders and we also run SHAP tests to understand what drives effects. And I'll talk more about SHAP in the results section. We also apply dummy outcome tests where no signal should exist. And these checks verify that CAST is not hallucinating and that the temporal patterns we recover reflect real causal signal. Next slide, please. Yes, so formally, we model a treatment effect as tau of x and t, which represents the causal effect for a patient with features x at time t. So instead of treating time points independently, we treat them as samples from an underlying function. So we're essentially going from disconnected points to a continuous curve. And this is kind of demonstrated on the two figures on the right, where we have a data point at every time horizon in intervals of 12. And the CAST, function will connect the points together. And each time horizon has a standard deviation, which is represented by like the black lines. In the next slide, I'll talk more about the parametric modeling and the non-parametric modeling, and then the two estimates we use SP, which stands for survival probability, and then RMST, which stands for restricted mean survival time. Next slide, please. Yes, so we use two complementary approaches to model this curve. First, we use a parametric quadratic model, which gives us interpretable metrics such as the peak time, maximum effect, and half-life. The second modeling approach we use is a non-parametric spline, which is a lot more flexible and can capture complex patterns. And when both of them agree, we have very strong evidence that what we're seeing is pretty intuitive. However, when they differ, that tells us something interesting is happening, and we should look deeper into the issue. So seen on the images on the right, the top one is the parametric model, where, as you can see, it represents more of a quadratic figure. And then the bottom one is a non-parametric spline. And as you can see, there's a little bit of a curvature in the middle. which is interesting, and we looked a lot deeper into the issue. Next slide, please. Yeah, so one technical challenge we ran into a lot in this project is that treatment effect estimates across time are correlated. So instead of fitting with standard least squares, we used a covariance aware approach, or generalized least squares. And we also apply this shrinkage to stabilize the covariance matrix. So overall, like, there's a lot of content on this slide, but the key idea is just to get a stable, reliable trajectory. And the technique we use is Ladois-Wolff shrinkage, which essentially helped us stabilize the covariance matrix. And the idea is to shrink the sample covariance matrix towards the scaled identity matrix. Next slide, please. Yeah, so I just talked a lot about the CAS framework itself, and we got some interesting results that I'll share now. Next slide, please. So before diving into the results, I want to give some more context about the RADCure dataset. I think Igor might have mentioned it briefly, but essentially what it is a Canadian dataset containing 2,600 patients with head and neck cancer, and the dataset originates from the Princess Margaret Cancer Centre from Canada. So all of the patients received radiotherapy, and about 37% also received chemotherapy. And even in the simple Kaplan-Meier curve, we see differences, but those are confounded. So what we do is we use causal methods to estimate the true treatment effect. And as seen in this bar chart here, as delineated by the key, the blue and pink are higher stages of cancer, and the y-axis represents the fraction of chemotherapy treated patients. And as seen in younger age groups, they're more tolerable and to this chemotherapy treatment, whereas older groups are not able to receive as much treatment. Next slide, please. Yeah, so something else that's important is addressing confounding, and we do this by using propensity score modeling. So in the data set, the treatment of chemotherapy is binary, right? It's yes or no, and it's also not randomly assigned. So what this tells us is that younger but sicker patients are more likely to receive chemo, which is what I just explained in the last figure. But also the propensity score is, it's delineated as probability of chemotherapy given patient characteristics. And the 18 covariates used in the study are age, sex, HPV status, cancer stage, smoking, etc. And however, many patients have extreme propensity scores, either really, really close to 0 or really close to 1. Next slide, please. Yeah, so this slide is really dense, but essentially we use a couple techniques to counter these extreme propensity scores. So clinical decisions based on patient characteristics tell us that some patient subgroups almost always get treated with one option versus another, leading to propensity X being really close to 1 or 0. And this is a violation of the positivity assumption. So what happens with inverse propensity treatment weighting? So when the propensity of X is really close to 0 or 1, the weights become extreme. And this results in high variance and unstable estimates, bias, etc. So some of the solutions are to trim, cap, or overlap weights. And trimming and capping extreme scores can work, however, it's somewhat ad hoc. So the majority of our approach was using overlap weights. So very quickly, how it works is for treated units where A equals 1, the overlap weight is equal to 1 minus propensity X. And for the control units, it's just equal to the same. You don't need to do 1 minus. And the properties here is that no trimming is needed, so it keeps all of the data. And also patients with propensity X near 0 or 1 get near 0 weights. So this is known as down weights extremes. And then patients with propensity X more closer to the middle, 0.5, get the maximum weight. And this is known as up weights overlap region. And the overlap weights estimate is not average treatment effect, but it's actually known as average treatment effect for the overlap population, or ATO. Next slide, please. Yeah, so here is a table kind of showing some of the results we got. It shows the estimated chemotherapy effects at different times after treatment. As you can see, there are several rows, each at every time horizon, starting from month 12 all the way to 120. in intervals of 12. Also, we include the restricted mean survival time and then also the survival probability along with their respective standard deviations or standard errors. Sorry. Next slide, please. Yeah, so here's kind of the key result we got from our experiments. We learned that chemotherapy survival probability benefit peaks around 51 to 64 months, and it provides a durable, not just early benefit. So as seen in the figure here, it peaks at around 5 years and supports long-term follow-up protocols. And late decline may reflect toxicity or competing risks, and the benefit remains positive even at 10 years. So as seen in this, like it represents the non-parametric, which is shown in red, and then also the parametric, which is shown in blue. And for the most part, the results agree pretty well. Next slide, please. Yeah, so who benefits most? Here I'll talk about the effect modifiers. So we also ran a bunch of SHAP tests, which is not really a causal method, but more of a method to tell us like which factors matter the most. These Shapley additive tests originate from game theory, but they've expanded into oncology and they're really useful. So we wanted to validate our experiments, and as seen in the matrix here, the two most important factors are age and HPV status. And this intuitively makes sense because for age, younger patients show larger treatment effects, and then for HPV status, like HPV positive patients will benefit more from the chemotherapy. And these are just potential causal effect modifiers, not just prognostic factors. And they tell us who benefits from treatment and not who has better prognosis. So if you look at the figure on the right here, you can use the heat map or the density to see which factors matter the most in terms of like chemotherapy treatment benefits. Next slide, please. Yeah, so there's a lot of slide or text on this slide. So here we just essentially do a bunch of validation, which is like the bottom section of figure 1 that I talked about. We have several methods, but essentially the goal of this is we need to ask, how do we trust our results? So unlike prediction, we don't observe the true causal effect. So we rely on validation and refutation tests. And we use several strategies. First, placebo tests, where we shuffle treatment or outcomes and expect zero effect. And second, we use synthetic confounders to test sensitivity to hidden bias. And then third, we use noise variables to ensure robustness. Here we inject random features into the covariate set, and the effect estimates should stay the same. And lastly, we bootstrap for stability using a k-fold CV or bootstrap resampling. And together, all of these techniques give us confidence that the effects we're seeing are real and that CAS is not hallucinating or giving us fake, inaccurate results. Next slide, please. Yeah, so now I'll give it to Igor to talk more about extending CAS to gliomas.
Yes, thank you, Everest, for going over CAST. So definitely CAST is not a disease-specific method that can apply to other cancers, potentially other diseases. So the next extension of it was to gliomas, lower grade gliomas, actually. So this is a type of brain cancer. So many people are more familiar with glioblastoma, which is the most aggressive and more common type of brain tumors, usually in older people and unfortunately with very poor prognosis in general. But these lower grade gliomas have a different biology. They have a mutant, this IDH enzyme is mutant. They behave differently and usually more favorably. So overall survival is usually 10 plus years. They can happen in younger patients than glioblastoma. But the reason why we studied it here is that what's the optimal treatment is not yet determined very well. So usually what is done is maximum safe resection, surgery, and then just observation or just this vorasidenib drug, which is an inhibitor of that mutant enzyme. And also radiotherapy and chemotherapy can be considered for these tumors. So those are what we investigated here. So our questions were, How does chemotherapy benefit for lower grade gliomas? How does that evolve over time? And also the same questions about radiotherapy. So the data that we used here, it's the Cancer Genome Atlas, TCGA. So this is a US-based NCI type of database for lower grade gliomas, and also an Asian version, Chinese Glioma Genome Atlas. As you can see, this disease is not very common, like not as common as head and neck cancer, for example, so sample sizes are generally lower. But our colleague here, who is at Memorial Sloan Kettering, he is assembling a larger data set. That's what we are planning to analyze next. And the graphs on the right, these actually show not the cast yet. These are just the raw causal survival forest estimates. They're shown without error bars because so you could see the subgroup effects. So the different trajectories are for different subgroups like male, female, age, less than median, greater than median, and so on. So you can see some heterogeneity, although the honest answer is that with these sample sizes, we could not resolve them with confidence, like this heterogeneity, but the method itself allows to do that. And also what we found is chemotherapy effects seemed strong, like the E values were 5 and over for those effects, suggesting that an unmeasured confounder has to be quite strong to nullify these effects. So we're pretty confident that these are realistic. And radiotherapy effect was much weaker. I didn't put it here, but E values are on the order like 1.6, 2, and something like that. So we reported those more as associations. And here is the application of CAST actually to the same data. So for chemotherapy, you could see that definitely the effects look big on the survival probability scale, like 30% or even 40% gains, although with big errors. And the profiles look somewhat different for the US and Asian dataset. Like for the US, you can see there is probably saturation or peaking suggested. For the Asian, not as obvious. But in general, this is an example of CAST utilization and generalization of the method beyond the specific results. And then we're looking forward, definitely our group is interested in continuing this type of research using CAST and other causal methods. And the ultimate goal of where we want to go with this is some kind of clinical decision support tooling, where of course the tooling is not doing the decisions on its own, but it's informing clinicians better. And the way we envision it is to combine a predictive layer with a causal layer and give both outputs to the doctor to inform in both directions. For example, given a specific patient presentation and features, the predictive layer would give some kind of estimate, like I just made up something here, 62% 5-year survival, of course, with some confidence interval. And the causal and cast layer would give some kind of treatment effect estimate, like say 12% at 5 years and 8% at 10 years, again with confidence intervals. So again, this on the right shows what is the difference in the distributions. So potentially a useful tooling would use both and inform the clinician with both. The code for CAST, which Everest developed and I helped with somewhat, is on GitHub. It's available. The causal survival forest is also available in the GRF package, and there is a publication for it. If anybody is interested in it, it's all available to read. RadCure dataset actually is also openly available from University Health Network in Toronto. We originally got it because we knew the investigator from there, but essentially anybody can also analyze this data set. Then these publications that we mentioned. Also in our group and department, we are continuing with this work. Like recently, I got a grant from Empire AI organization in New York State to get a postdoc to do this kind of research for 2 years. So we're hopeful for that. Actually, just hired the person. And of course, we're trying to connect and keep collaborating with people who are experts in the causal field and medical AI field. You could see some of them here, and some of them definitely from the US, but also two from Germany, as you can see. Professor Feuerriegel and Spindler are from Munich and Hamburg, and they're also very interested actually to apply these methods to medicine, which I think is promising. So the general conclusion message is that prediction and causation are not the same. Both are important, but they're distinct. We think both of them are definitely needed in medicine. Mechanistic understanding, we think, also strengthens the foundation and interpretation. So here we used it in the head and neck example to design that biologically effective dose variable, which was the variable for the treatment. It is also valuable to estimate heterogeneous treatment effects, not just average treatment effects, and the time trajectories as well. And of course, education of new generation of scientists is very important, and I think Everest is a great example of this, of a motivated student who is interested in this type of research and accomplished already a lot of publications at good conferences and journals. So thank you very much for your interest. We look forward to your questions, to communicating more. Our emails are here.
Amazing. Thank you very much. If anyone has questions, you can raise your hand or just speak up. You can also put questions on the chat. Yeah, Kimberly, please.
Hi, thank you for the talk. My questions are to Everest. So my first question is, from both of your talks, my understanding is, so you use between about 800 and 2,600 patients. So I was wondering if you thought there was a lower limit at which it was still possible to use this technique. So for example, would it be feasible to use it with 500 patients, 300? At what point would it just not be feasible because the sample size is not big enough? And my second question is, I really loved how you showed the error bars, because as your senior researcher was saying, it's so important for reproducibility to be honest about error. But I wondered if anybody had pushed back about how big those error bars are, because often in science people don't like such huge error bars, and how you answered that kind of point.
Yeah, so for the first question, I think I don't really have like a definitive number for you, but I think obviously the more data you have, the better, unless like you start to see that the data is overfitting. Like for example, if you only have 10 data points, right, the CAST framework is not gonna prove well. So I guess my advice would be just have a good amount of data to show. And then the second question could you repeat it? It was about error, I think.
So how huge your error bars were. So I really love that you have such huge error bars. I think that's really important in science, that we are honest about showing uncertainty. But especially in my field as not a statistician, but someone from a clinical background, sometimes people don't pretend, they don't show that kind of error. So I was wondering if anybody had shown surprise at how big the error bars were and how you would rebut them and say how important it is, that it's normal to have such large error bars.
Igor, do you remember?
I can help. I mean, with these questions. So the first one, I think about sample sizes, as Everest said, I think there is no clear cutoff. I think practically in our experiences that maybe 500 patients for average treatment effect might be sufficient. Probably what limits is a lot is this positivity propensity score issues. Like if there is good overlap, essentially that assumption is saying that each covariate profile should have a probability that's not extreme, not 0 and not 100% to get each treatment. In reality, as we showed for the head and neck cancer, that's often violated a lot. Like a lot of patients get extreme scores because the clinical decisions are tree-like. So I think that is a limiting thing. But for average treatment effect estimation, a few hundred patients could be enough. For heterogeneous effects, honestly, usually that's not enough. You probably need thousands of patients to really resolve subgroups. So that would be the question. The error bars, I think, yes, we need to report, like as you noticed, for example, for the head and neck cancer, they were smaller because there was about 3,000 patients. For the gliomas, they were definitely big. We realized that these are, in a sense, preliminary. That's why we're gathering with colleagues more data on this disease. There is less open source data, there is more proprietary and privacy locked data, so that's why it's taking longer, but we definitely want to continue analyzing it.
Thank you very much. Maybe we have time for more questions if you have any. If no one, then I have a couple of questions. So I think my first question is that I really like that, well, about the clinical insights. So I really like that it's very practical approach and that from the cost model, you actually get something which is very actionable. And in your work, you also demonstrated that you were focused on getting some clinical insight from your results, which I think is really, really good and important, and not always I see in some papers that they actually do that. So, and I do see that there is value in just having the idea about where the saturation point of the treatment is, and perhaps related question, like, do you think that have you experienced that quadratic function is basically enough, which pretty much allows this shape where there is a saturation point just because you use quadratic spline for that? Or is it like basically is the saturation point is kind of the by design, or is this is something that you would see if you like use non-parametric model as well? And I guess the second question is also, I think there was a good example about how causal interpretation is important. That, for example, younger age is not that younger participants benefit better, but it's more that it's more causal. So it's not the prognosis is better, but they do benefit better. So that's a very good example. I wonder if CAST can somehow be also used to compare different treatments, not just to compare different features of patients, but to compare treatments. Thanks.
Yeah, thank you for your interesting questions. Definitely, we're trying to go to actionable type of recommendations, of course, realizing the limitations of the data and so on. I didn't mention this here, but for example, for the head and neck cancer, the action where this is pointing is towards this higher intensity treatments, which in practice would mean hypofractionation or twice a day fractionation, in a sense. So these simulations, models, they point to, for example, if you treat the patients twice a day with smaller fractions, you would get bigger treatment effects. Logistically, this is not realistic. This is another practical thing because neither doctors nor patients want this. Because patients would have to wait the whole day because you need repair time between fractions. And doctors, this messes up their schedule completely. But then the next thing would be hypofractionation, so bigger fractions per day and fewer overall fractions, so shorter treatment regimen. So that is the insight that we're trying to communicate based on the CAST application for the head and neck cancer. And in general, I think the field is thinking about this seriously. There are some clinical trials starting, not specifically, of course, because of our publication, but in general, it's pointing that way. For the glioma, I think it's also concordant with what the field thinks, that radiotherapy role may not be that strong for this specific disease, for the low-grade glioma. It's probably more targeted therapy. This vorasidenib, there was a trial showing that it's really beneficial. And like our results in a sense, reproduce that and reproduce what the RCTs showed, but on observational data as well. So I think it's useful. Regarding comparing different treatments, that is an interesting extension where we want to go. Like in a sense, for now, causal survival forest, like we used it in binary setting. So for example, for head and neck cancer, it was just radiotherapy alone versus radiotherapy with chemotherapy concurrent. Those were the binary options. We could extend it to discrete treatments, for example, or potentially to continuous. I mean, definitely that's something we're thinking because continuous treatments in medical settings definitely common in radiation, but also I'm sure like what your group is doing too, because it's dosages of medications. So definitely that's something to develop, to consider.
Yeah, absolutely. I think for mental health, there are lots of treatments that are continuous, or number of sessions that they receive, for example, for psychotherapy or the dosage. Yeah, so that's definitely applicable to mental health. And I think also like for all the new interventions is always like one of the questions, like, is this better than treatment as usual? Is this better like between A, B, C, D, etc.? So that's kind of one of the main decisions for like clinicians often to decide which route to go, and it may be more than two. Yeah. So I think that's going to be a very interesting extension for this approach. Yeah. So I wonder if maybe more questions from the audience. If not, I think that we already overrun a bit. If not, then I think we will all like round of applause. Thank you very much for everything. Thank you very much for the very interesting talk. I definitely think that there are many ways to apply like more actionable insights, and I'm quite impressed that it really gives some clinical implications that you can see it from applying CauScien to real medical data.
Can I just wanted to say thank you for the talk, but also say that I got cut off halfway through the talk and I missed quite a bit before I was able to rejoin. Unfortunately, we had a major power cut, and it affected the internet. So, when previously I've tried to access recorded talks, because I'm part of UCL, I haven't been able to. I just wanted to ask whether the speakers were okay with uploading this to something like Dropbox, so we can listen to the talks later.
Yeah, of course.
Sure, you mean the slides? Like we don't have the recording, we have the PowerPoint presentation. We can upload that.
Yeah, I mean Diana would have the recording, I believe, but I can't access it the normal ways because I'm part of UCL, not King's College. And at some point, if you don't mind, I will get in touch with you, Diana, and Igor, and Everest to actually talk about application of this in Alzheimer's disease. We have access to clinical trial data that might be really useful, especially if there is a way of doing this as a meta-analysis.
Absolutely. I think all the talks are uploaded to the YouTube channel, so even the previous ones. So if you're looking for some of the previous ones, they are on the YouTube channel for the prediction modeling presentation. It will take some time, so if you want it sooner, I would share you like in Dropbox, but at some point they're all there basically.
Okay. Thank you.
Yeah.
Yeah, thank you for your interest. Definitely, we're open to discussing more. I think this can apply across different diseases for sure. And also for not only for observational data, but for clinical trials as well. I think where it could help with the clinical trial data is the subgroup identification.
Yeah.
Because the average treatment effects you already know, but the subgroups, probably the trial was not designed with many subgroups in mind.
Yes, yeah, that's right. Yeah. Thank you.
Yeah, thank you very much, Miriam. Sorry about your interruption.
Yeah, thank you very much for having us. And
Bye-bye.
bye-bye.